1, 2.
Yep, there you go.
Good. Okay. Great. Okay. Right. So the talk is about planets and exoplanets. So with my slide a little bit. Yes. There we go. So quick history lesson. This is the state of our knowledge of planets and planetary systems circa 30 years ago. So just one planetary system known, our own solar system. And in 1995, that changed with the first discovery of an exoplanet around a sun-like star, bringing us to today, where we now have over 6,000 known exoplanets, according to the NASA Exoplanet Archive as of yesterday evening. So what's the takeaway here? There is an immense diversity of planets that populates our galaxy. When we compare against our solar system, which is a relatively ordered place with its close-in small terrestrial rocky planets, there, small terrestrial rocky planets, and its outer giant planets. So this diversity is apparent. It gives rise to whole new classifications of planets that we never knew of before. Hot Jupiters, the topic of the talk today, Sub-Neptunes, and I'm not explicitly going to talk much about super-Earths, but these are both, Sub-Neptunes and super-Earths are both planets that are intermediate in size and mass between Earth and Neptune and Uranus. So what is not apparent from a scatter plot like this is any real meaningful information about the underlying intrinsic occurrence rates of different types of exoplanets. And that is because all of these different detection techniques carry with them very severe intrinsic biases. So we need to account for those biases to recover the underlying exoplanet population properties. And we can do that with a well-defined sample. So NASA's Kepler satellite provided just that. It was a well-defined experiment staring at a set of 100,000 stars for a well-defined period of time to look for transiting planets. So we can back out the intrinsic occurrence rate here of planets with orbital periods less than 100 days, because that's the range of orbital periods over which we have sufficient completeness in our data. And this is the result of that exercise. So now we see that among close-in planets, the large giant planets are intrinsically rare, and the smaller planets are intrinsically common. More interesting perhaps than that is that there are two types of small planets. I'm going to give them some names now. I'm going to posit that the first peak in this distribution is the rocky so-called super-Earths, and the second peak is what we're going to call sub-Neptunes, which are presumed to have gaseous low-density envelopes, right? Larger objects are the ones that are bigger because they are puffier, they are lower density. The smaller family of objects, they're smaller because they're dense and rocky. And then we have a clear bifurcation between the two families of planets with what we call the radius valley, a region of low intrinsic occurrence rate in between. So I'm going to spend the rest of this talk, this whole family of exoplanets that I could have chosen to talk about. I decided that I wanted to spend this time speaking to you all about the Sub-Neptunes. I love Sub-Neptunes. You should too. And why? They are the most commonly occurring type of exoplanet that we know of today in our galaxy. They do not occur at all in our solar system, so this is a fundamentally new class of exoplanet. And some of these planets are readily observable and characterizable today with JWST. All right, so I'm going to back up and motivate what some of the key scientific questions are that we wish to address with this population of planets, and really essentially with any new population of planets, but for this population of planets in particular. So I broke this down into three categories. We want to learn about formation, evolution, and habitability. So formation is basically how did the planets form, where did they form, under what conditions, and this is basically, formation gives rise to the bulk composition of an exoplanet. Evolution is a particularly important topic to consider for sub-Neptunes. So when I talk about evolution, what do I mean? Processes like mass loss, processes like interactions between the outer atmosphere of the planet and its interior. We think that this is a key critical process that ultimately defines the composition of a sub-Neptune atmosphere. So we're going to be talking a lot about these kinds of evolution processes. And then habitability, a key goal of the exoplanet field is to push towards the study of habitable environments, eventually find life or signs of life on an exoplanet. Sub-Neptunes are very useful stepping stones towards that goal. They are smaller and often cooler than the hot Jupiters, which have been kind of the early targets of atmospheric characterization studies, because those are the highest signal to noise, the easiest targets to do atmospheric studies for. But now we're pushing towards these smaller, cooler objects, which is eventually going to step us all the way towards characterizing habitable environments. Along the way, maybe some of the sub-Neptunes themselves present habitable environments. I'm not going to talk too much about that today, but feel free to ask in the question session. And addressing all of these questions motivates atmospheric studies because spectroscopy, people were just poo-pooing spectroscopy during the cookies upstairs, but spectroscopy offers very information-rich data about things like composition, temperature information, et cetera. So we're going to use spectroscopy, studies of the outer envelope, the atmosphere of the planet, in order to try to address these key questions. Okay, but there are problems. Here's the first major problem. Without our atmospheric studies, when we just detect an exoplanet, measure its mass, measure its radius, and we can plot these planets on a beautiful mass radius diagram, and we can already learn something about the bulk composition of these planets through their bulk density. This is how it was confirmed that the hot Jupiters are indeed gas giant planets. The first transiting hot Jupiter was the first time we had a measured mass and radius, and then you could confirm that this is indeed a bulk hydrogen-rich object. But for the sub-Neptunes, they live in this horrifically degenerate parameter space. So these are curves of fixed composition, so Earth-like composition, pure water planet, pure iron planet. And if you look at any one of the points in this region, the sub-Neptunes, you can convince yourself very easily that you can fit the bulk density, the mass and the radius of the planet by two competing families of models, right? One that would be a solid rock iron interior with a hydrogen-rich envelope, a whole different family of models that would be made up more in bulk by moderate density material like ice, like water. So with mass and radius alone, we can't really even distinguish what these planets are built of in bulk. Again, requiring atmospheric studies. All right, so I'm going to step through briefly the formation and evolution aspects and how they apply to sub-Neptunes, what kind of specific studies we're going to want to do. So from a formation standpoint, just in a really basic sense, two competing models for sub-Neptune formation are an in situ formation model, where the planets would be built primarily of rock and iron in their interior, and then they accrete thick, moderately thick hydrogen helium atmospheres, primordial atmospheres. A second competing theory is that these planets are formed initially farther out in the disk, out beyond the water ice line. There they would have access to large amounts of water ice at formation. They'd be very water rich in bulk, and then the planets migrate in later. And these two competing families of models would be accompanied, at least at first glance, they would be accompanied by very different atmospheres, right? A primordial hydrogen helium atmosphere with something like solar composition gas versus a water-rich composition. Turns out it's a little bit more complex than that, but these were kind of the simple models that we started off with back in 2009, 2010 when we first started thinking about these planets. And there might be some evidence that both families exist. So this is an interesting result from a science paper from a few years ago now, looking at a set of low mass planets orbiting M-dwarf stars. And the authors are making an argument that there are two populations of sub-Neptunes, a set that is consistent with being so-called water worlds. And this composition line, this density, is specifically for a planet that is 50% water, 50% rock and iron with Earth-like ratios of rock and iron. So that's their classic water world, half water, half rock iron. And then these guys are the so-called gas dwarf planets with the rock iron interiors and the hydrogen helium atmospheres. It's unclear whether this really holds up. Mm-hmm.
Why would anybody, this is a naive question, why would anybody assume there couldn't be both? Like, were people actually advocating that it could be one or the other, or?
I mean, there could be a dominant formation mechanism. I mean, we've never seen a water world before. Maybe Arc, the Neptune and Uranus are sort of water worlds, but they have water and hydrogen helium.
Yeah.
Yeah, so I mean, it's not crazy that there would be both, but there may be a dominant.
Yeah.
There may be a dominant mechanism, and it may be that the relative prevalence of these different types of planets depends on stellar host type. So this study was specifically done for planets orbiting M-dwarfs. It's not clear that you get the same kind of population around.
No, my assumption is
stars.
because of star types and different orbital radii, you would have all of them, but this is not my thing.
Potentially. So yeah, this is part of what we want to probe. Okay, to make matters even more confusing, so I'm part of an exciting collaboration right now, led by Ted Bergen at University of Michigan. Jackie Lee, the first author, is actually a high pressure experimentalist, where this is a group of people who are considering the implications of having carbon involved in bulk in the formation of planets in general. The picture here is that you have involatile carbon grains present in the molecular cloud as the star and disk are forming. As long as those carbon grains are not irreversibly destroyed as you're assembling the disk, then they're going to be incorporated into the planet itself. And there is evidence that you could have very high abundances of these carbon grains present at formation, then get incorporated into the planet. So now we have to account for not just rock, iron, water, and hydrogen, but now we have to account for carbon solids as well. And so we've been arguing that you can't actually assemble a water world without also incorporating at the same time a large abundance of carbon in the form of what we're calling it soot. Also, even interior to the water ice line, you would still have carbon solids in stable form, and so you could form a so-called soot world, a carbon rock world.
What's the difference between soot and pot? I mean, like, is soot bigger?
They're potentially they're in the same family of materials. We don't exactly know what phase the carbon will take on in the interior of a planet. That's part of why Jackie Lee is involved in this work. So she's a high pressure experimentalist who's gonna put the carbon under pressure, and we're gonna look at the carbon phases. Yeah. Another question. Okay. Oh yeah, and the implications are that, again, when we look at one of these mass radius diagrams, now, for example, the planet that was previously well described by the previous paper as being 50% water, 50% rock iron, can now also equivalently be explained by one of these soot water worlds where it's, 25% water, 20% soot, and half rock. So we have even more degeneracy, which just further motivates that we need to look at the atmospheres of these objects to try to distinguish different families. Evolution. So it's not just formation. We need to think about everything that happens after formation. Early on in the history of the exoplanet field, when people were first building interior structure models of exoplanets, they tended to build models like this one, layered. So start with the metal core, then we put the rock on top, then we put a water ice layer on top, and we put a hydrogen helium layer on top. This is motivated by our understanding of the structure of solar system planets. But when you consider the both the increased mass of a sub-Neptune, the fact that sub-Neptunes, at least transiting sub-Neptunes, tend to be close in, they're highly irradiated, you end up inferring a structure that's maybe more like what's depicted here or here. So you heat up all of the layers, you can heat things up to the point where the various layers can become chemically miscible with one another, so you don't have clear distinctions between, say, the water and hydrogen layer, or even the water, hydrogen, rock layers. And in between, we have the scenario that we think is very relevant for a lot of sub-Neptunes, which is one in which the planet is hot enough such that the rock melts into a permanent or semi-permanent magma ocean with an overlying atmosphere that could be mixed water and hydrogen. Water and hydrogen become miscible at high temperatures. And the magma ocean paradigm is very interesting because it allows for ready chemical mixing between the atmospheric envelope and the interior of the planet. So now the atmosphere, the composition of the atmosphere is governed by its chemical interactions with the interior. All right, we also have to think about mass laws. So back to the spot from the beginning and the radius valley, why do we have these two distinct populations of planets with the radius valley in between? There are many papers that show that you can very naturally form the two distinct populations of planets if you consider the effects of mass loss. So the rocky super Earths are the ones that have catastrophically lost their primary atmospheres. The sub-Neptunes are the ones that are somewhat more massive, maybe slightly less irradiated, and so they've retained primordial atmospheres. There are several potential mass loss mechanisms. You can lose an atmosphere via photoevaporative mass loss, via core-powered mass loss. So core-powered is the bolometric, is mass loss via the bolometric luminosity of the planet itself when it's very young and still hot from its process of assembly and accretion. You can also have a mass loss that's driven by impactors. And all three of these mass loss mechanisms have been shown to generally reproduce the properties of the exoplanet population in terms of their size distribution. So now the question is, which of these mechanisms is consistent with the population in terms of what we see in their atmospheres? So we need predictions from each of these different mass loss mechanisms of what that does to the composition of the atmosphere that we observe, say with JWST. Those predictions mostly don't exist in the literature yet. So one thing that I've been trying to do is motivate people to give us some predictions. This is some early work by James Owen that he's shared with me. It's a very theorist plot, but basically what we're seeing here is this hydrogen depletion factor. So think about the planets to the right as being younger, and the ones to the left being older, so they've lost more of their primordial envelope. And then we have mass loss rates for different neutral and ion versions of hydrogen, carbon, oxygen. So the key takeaways here, there's two. One is that metallicity goes up with increasing mass loss. So the more you depleted your hydrogen, basically the older your planet gets, you're losing hydrogen very quickly. And so that is going to, and you're losing hydrogen relative to oxygen and carbon and heavier species, right? There's fractionation occurring. So metallicity is going to go up over time as the mass loss, and this is all for photoevaporative mass loss. So as photoevaporative mass loss proceeds, your metallicity is going to rise. Also, the second really interesting results of these calculations, which is that they're showing that carbon is being lost at a much higher rate than oxygen. The reason for this, there's not a strong mass differential between carbon and oxygen, but carbon is much more readily ionized, and then it gets more readily entrained in that outflow. So you lose carbon faster than you lose oxygen, and therefore you end up with a carbon to oxygen ratio in the atmosphere that goes down over time as mass loss proceeds. So these have observational consequences, right? We can observe spectroscopic features of carbon and oxygen bearing species.
Yeah, but there's no time scale on this plot. Can this happen immediately?
There is no time scale on the spot, that's correct. This is not, from my understanding, this is not a full time-stepped evolution model. They are working on, so there's no real quantitative predictions yet of this of this framework. They're working on that. Mm-hmm.
Maybe that's the answer, but is the idea that it's from the quiescent state of the sun, or it's like driven by flare activity and stellar activity? Like, is it stochastic or steady state this whole time?
I think this is effectively a steady state model. Yeah.
Well, the model is, but what about the physical reality?
Oh, the physical reality is, yeah, probably more individual flares. Yeah. I mean, there's an average over time, but yeah. Yeah, so this model is basically predicated on the fact that mass loss is occurring, and so you are depleting atmosphere over time.
Because like the range, it's the wind, not the photons, right? That are.
It's photoevaporative, so it's the high energy photons.
It is.
Yeah. Yes.
And you talked about the sub-Neptunes for being formed beyond the suit line, and so if they are losing the carbon due to their formation as having increasing mass loss, is the only observable on the planet itself, or can you also say something about the environment the thing is in? Like, could we see remnants in a disk where this carbon emission or something?
So the atmosphere studies are typically done for systems that are evolved on the main sequence. So we want to kind of put both pieces together. Right? We want to put the protoplanetary disk studies together in context with the exoplanet atmosphere studies. And then I should say this was done for an initial mixture of solar composition gas. So these calculations don't account for the soot line and that extra carbon that may be present in formation. Okay, so I want to get to the JWST results. So this is kind of background. So part one takeaways is basically this is I think there's a really classic kind of progression of fields in astrophysics, right? The old static picture has been replaced by a new dynamic picture of sub-Neptunes, where now it's not just they formed and then this is what they're made of forevermore. Now we have to realize we have to consider processes like magma-ocean interactions, mixing between interior and atmosphere and mass loss. So yeah, now I'm going to pivot to actually looking at some of the results from the atmosphere studies with Hubble and with James Webb to see what we've been able to do to begin constraining this whole picture of sub-Neptunes. First, just a quick primer on techniques. So I'm talking today really exclusively about transiting exoplanets. So the atmospheric studies that we are doing are taking advantage of the transiting geometry of the system. So I'll talk about transmission spectroscopy, where we're taking advantage of the planet in transit. When it passes in front of its host star, some of the light from the star is going to get absorbed directly through the atmosphere of the planet. You get an absorption fingerprint of the atmospheric composition of the exoplanet. The other technique I'm going to talk about today is the phase curve, the orbital phase variations. So first, let's think about the secondary eclipse planet. So now we're observing with JWST, so in the infrared thermal emission, when the planet disappears behind its host star and then reappears, that gives us a differential measure of the thermal emission from the planet's day side. Now let's just keep observing and watch the planet go around in an entire, again, we're not resolving the planet from the star, right? We're just seeing the combined light of planet plus star as the planet orbits all the way around. And you can see that thermal emission go through phases as the day side and then the night side of a typically presumed tidally locked planet, if it's close in, right? Presumed tidally locked planet shows you its different phases. All right, first, there'd be more dragons. So the very first observations of sub-Neptune atmospheres were made not with JWST, but previously from ground-based observation with the VLT. And then this is now a very famous observation from Hubble that stacked 12 transits of one planet all together. But this was needed to build up signal to noise. So what we see from all of that exquisite data is a very, very featureless transmission spectrum. Do not tell me that we did not measure anything here, okay? Sorry, I'm a little bit defensive about this because I get this question all the time. This is a very, very precise measurement of the transit depth of the planet. So how much light was blocked by the planet at each of these wavelengths. And what this is saying is that each and every wavelength band, that planet blocked out basically the same fraction of the starlight. Whereas if we were seeing absorption through gases in the atmosphere, we would have seen a wavelength dependence to that measurement, and did not. So what does this tell us? The spectrum is so flat that it basically rules out all plausible molecular compositions of the atmosphere. And what we are left with is a conclusion that the planet is obscured by a layer of clouds or hazes. So I'm going to use the term aerosols to refer to particles in atmospheres. A cloud is something that condenses directly, like our water clouds. A haze is something that is formed through chemistry, typically photochemistry. So think like, in Earth's atmosphere, think like smog, or in Titan's atmosphere, I think of its hydrocarbon haze, and that's going to be a good analogy for sub-Neptune aerosols. And we know this planet has an atmosphere because it has a low enough density that it can't be a bare rock. So it has to be that it's being that the light's just being blocked by an aerosol layer. So this is the problem. This is not good if we want to detect gases in exoplanet atmospheres.
The idea that the haze or aerosols are prevalent throughout the atmosphere, even as you go up in height above the surface, or is there a cloud deck or something where there's some atmosphere above it, but not much?
Yeah, all we know here is that the optically thick cloud deck is high enough up that it's that basically it's creating a photosphere well above where the photosphere would be for the gases.
Any atmosphere above that would be
just optically thin. Yeah. So the implied pressure of the optically thick cloud deck in this case is as a pressure lower than like a millibar. And it's actually really difficult to build models that get enough of any kind of aerosol up at that location in the atmosphere.
And how is this different than Neptune?
Neptune, I think that if you put Neptune in transit, well, Neptune's colder, so it's just, its scale height is all smaller, so its features would be smaller, but otherwise, Neptune, you would still see gaseous absorption through Neptune's atmosphere. So, yeah, the clouds that you see in like the giant planet atmospheres in our solar system are not so thick, so high up.
They're not, yeah.
Yeah.
They're not.
Yeah. Yeah, so it's the fact that they're very optically thick at low pressures.
Because there's like the comparative plot of all our planets in the near infrared, and there's features all over the place, right?
Yeah, model transmission spectrum models of our solar system planets produce, like, none of them produce flat spectra like this.
So you depict.
Unless it's Mercury and it has no atmosphere.
So are there lines detected at any transiting exoplanets?
Oh, yeah, sorry. Gosh, I don't want to be so pessimistic. Yes, so in hot Jupiters, and we'll get to other sub-Neptunes where we see features. This was just unfortunately the first sub-Neptune that we looked at. And when we thought we were going to do all this exciting science with figuring out its bulk composition and how it formed, instead we learned that aerosols are an important piece of chemistry and physics that we need to understand if we want to understand the atmospheres of these planets. I spent probably at least a decade of my career like exclusively on the aerosol. I'm not gonna show you all those results because I want to get to the JWST results. This is an empirical result. This is an observational result summarizing all of the other planets that were observed with Hubble prior to JWST. So the y-axis is basically the size, the amplitude of the spectral features that were observed in a given sub-Neptune's atmosphere in units of atmospheric scale height, so that we're all normalized to a common scale, basically. As a function of planet equilibrium temperature, which we can basically think of this as the amount of installation or the amount of flux that the planet receives. So the interesting thing here is that we detect larger spectral features for hotter and colder planets, but for kind of moderately irradiated planets, we tend to get these very flat transmission spectra. And you can squint at this and decide if you really believe this parabolic fit or not. It's tentative, but it's motivational. Let's say
This is directly from the previous.
this is from many other spectra of this type. So
Yeah.
many, so like 12 other planets,
Yeah.
all observed in this wavelength range, where some of them did have spectral features.
Gotcha.
So we measure the amplitude. So for this case, this one would be a 0.
Show me what, so this one would be.
They didn't put that planet on this plot because its error bar is so tiny that it completely skews the fit. So they decided to not account for it.
Okay, so you are not on the same.
I'm not on this video. Okay. Oh gosh.
The water emission from an exoplanet means that the starlight is exciting it, is exciting the water molecules versus absorption.
So the transmission spectroscopy is an absorption only technique. You're just seeing the absorption by gas.
That's sorry. Okay.
Yeah, so these are the units here are kind of weird. This is basically effective radius of planet as a function of wavelength. Yeah.
Okay.
Yeah, so for the sample you showed, it's a variation in the equilibrium temperature, more of a reflection of the orbital distance where stellar hosts start.
Oh, that they're convolved together. So the hotter planets are in part hotter because they're closer in, and they also tend to be the ones that orbit the earlier type stars. So yeah, it's really hard to remove that bias. Given the kind of number of targets that we have available to us. We'd love to do that. Maybe we'll be able to do that. All right, oh yeah, the other point I wanted to make was that this trend kind of makes sense if you think about what could be forming the aerosols, so the picture that emerges here is that you would expect thick aerosols over this kind of temperature range if the aerosol is a hydrocarbon, is basically a hydrocarbon haze formed by initial photolysis of methane, which then tends to you'll make higher order hydrocarbons. They tend to polymerize, and you make like hydrocarbon gunk, like in Titan's atmosphere. So methane is not going to be the preferred form of carbon in atmospheres above a temperature of about 850 Kelvin. You'll get carbon monoxide instead of methane. But at lower temperatures, you get methane. You have UV from the star, so you photolize the methane and you build up these hydrocarbon hazes. So that's kind of that's the hand wavy theory picture of what could be going on here. So we want to test that. I don't have the ability to do all of the carbon chemistry necessary. Very few people in the astrophysics field do have the ability to do all of the hydrocarbon chemistry necessary to understand the formation of soot or hydrocarbon haze. I hired a physical chemist. Jae-Hyun Yang is my new postdoc. He was trained as basically in chemical engineering as a PhD student at MIT. So he has this neat idea where the hydrocarbon hazes are precipitated not actually by UV photolysis from the host star, but he pointed to some results in the chemical engineering literature that show that at the temperatures of the deep atmosphere, so where it's going to be much hotter in the sub-Neptune, you have appropriate conditions to make PAHs, high order hydrocarbons, hydrocarbon rings in the deep atmosphere just by thermochemistry. And then through mixing, through quenching and vertical mixing, you can loft those hydrocarbons up to observable locations in the atmosphere. There, the UV is going to play a role. So then you're going to have your photolysis. You're going to maybe make even higher order hydrocarbon rings and build bigger haze molecules. So he thinks that the thermochemistry in the deep interior plays a role. And this has some predictions where haze formation is going to occur most readily in high metallicity atmospheres and high carbon to oxygen ratio atmospheres. This is effectively just equilibrium chemistry. So we should see these kinds of, so this gives us some predictions for JWST, where not only should the occurrence of haze depend on how irradiated the planet is, but it should also depend on the underlying composition of the atmosphere. So this gives us some testable predictions. It might also explain why we have some scatter in the bottom of here, where we have planets that seem very hazy and not so hazy. That might be compositional diversity.
Right, so do we only see this trend on Sub-Neptunes? We don't see this temperature dependence on other.
We haven't, so for true giant planets,
Right.
we haven't really gone down to these lower temperatures. There's just not as many high single
manatees,
objects.
They see features in all, right?
I don't think they see features in all, but they might go down to like, I don't know.
Right, yeah, somewhere near that, yeah.
Here-ish, so they might see the onset of hazes. Also, there are predicted to be some surface gravity effects that might matter as well. And the compositions might actually be fundamentally different. The Sub-Neptunes might on average be higher metallicity. That's another.
Right,
another
yeah, I wonder like if the J-Hans simulation can be applicable to.
Yeah, it should be, yeah. Mhm. Yeah, we focus on the Sub-Neptunes, but we could also extend this to giant planets really readily. All right, so I'm gonna finish up by going through observations of 3 Sub-Neptunes with JWST to kind of step through from the high temperature to the lower temperature through this haze, this potential haze trend. So we'll start with the hot one, TOI 421b. So this was a cycle 1 program that I led because we wanted to observe a Sub-Neptune around that was hot enough that we would predict that it would not have hazes. Right, so We're over here where the planet should be too hot to have methane, should be too hot to form a hydrocarbon aerosol. So we're predicting clear atmospheric conditions in this temperature range, and there's the spectrum, and we do indeed see clear atmospheric conditions. So these are spectral features due to water absorption. So there's water vapor in this atmosphere. There's potentially SO2 and CO in this atmosphere, but those are very tentative. So we really need to go back and get more data to confirm the other molecules. But what can we, so we confidently detect water. We can infer the mean molecular weight of the atmosphere due to how large the spectral features are. That's tied to the scale height of the atmosphere, which is tied to the mean molecular weight, bulk composition of the atmosphere. So we infer a low mean molecular weight, consistent with like a solar metallicity, a true primordial atmospheric composition. And again, we infer aerosol free composition, at least in the observable atmosphere, right? There could be aerosols deeper in, but where the atmosphere is optically thick, so we don't see those. Okay, so what do we do with this spectrum? Right, this is the part where we want to tie it to formation and evolution scenarios. So this is work done by my former postdoc, Matt Nixon, where he wants to use the atmospheric measurements to constrain the bulk composition of the planet. So given what we see in the atmosphere and a model of the internal structure of the planet, we're basically bounded by two families of models. So basically what he infers is that this planet has a primordial hydrogen-rich atmosphere, and that atmosphere is about just 1% by mass of the planet, where the rest of the interior of the planet would be rock and iron. So this is really a classic gas dwarf scenario where we have a kind of Earth-like interior with a thin but still fairly substantial hydrogen-rich primordial envelope. This maybe fits with the in situ formation model. All right, next planet. GJ1214b, the one that I showed you previously with the exquisitely flat transmission spectrum. We decided, hey, let's go back and observe it with JWST, but we know that the transmission spectrum is very flat, so let's not do that again. Let's use the unique capabilities of JWST to observe the thermal emission from this planet. So this is a thermal emission phase curve. So what you're seeing here is this almost 2 full days of just staring at the planet plus star system. There's the transit in the middle. It's bracketed on both sides by secondary eclipses. So that's the planet disappearing behind its host star. It's the first detection of thermal emission from a sub-Neptune. So that was really exciting. And this measurement was taken at the very beginning of the JWST mission. So it's like July of 2022. So basically right after the science mission started, we got scheduled right at the beginning. So this was really fun. Okay, so we detect the thermal emission, we detect the secondary eclipses, and right away, we knew that something was interesting here because the planet was colder than we thought it would be. If we just calculate a 0 albedo temperature for the planet, assuming that it redistributes heat uniformly from its day side to its night side, then we would have gotten this phase curve. So it would have been hotter at all orbital phases than what we saw even on its day side. So this means that the planet has a non-zero albedo, which is somewhat surprising. And we want to use the phase curve to infer the composition of the planet's atmosphere. So this is where we need 3D models of the heat circulation on the planet's atmosphere and how that depends on the underlying atmospheric composition. So we turn to Maria Steinruck, she's a postdoc right now, a Joan Peg Fellow at U Chicago. She was and is the only person in the world who can do 3D general circulation models for sub-Neptunes with haze in their atmosphere, since we know that this planet has a hazy atmosphere. We need to account for that. So first, these are the clear atmosphere models with no haze. And you see they all provide a bad fit because they all produce a planet that's hotter than what we saw. They basically, the clear atmosphere models can't produce that high albedo. So now we throw the hazes in. And okay, so two results here. We get a better fit. So sorry, this is the fits of the data, and the colors are all. So the models that best reproduce the properties of the data require a very thick and very reflective haze, and they require a high mean molecular weight atmosphere. So basically a high metallicity, very high metallicity, like hundreds to thousands of times times the solar metallicity. You will note that none of the models actually fit the data. That is okay. So these general circulation models are computationally expensive. We can't run a whole parameter sweep. So we're just looking for families of models that provide an improved fit to the data. And that requires thick reflective hazes and high mean molecular weight composition.
Sorry, before you go, what is 3,000 times solar heats?
So it's basically up the abundance of everything except hydrogen, helium by a factor of 3,000 relative to hydrogen, helium. So this is now no longer a hydrogen dominated atmosphere. This is not necessarily a realistic scenario. Like it's hard to imagine how you would just lose hydrogen to that extent without changing the abundances of the rest of the species. So this is kind of it's a way of parameterizing an increased mean molecular weight relative to solar.
What's for purpose?
In terms of a metallicity relative to solar, I don't actually know. But it would be, it's weird to even, because the other right, like carbon, oxygen, nitrogen aren't necessarily in solar composition. But it would be higher. It would be higher than 3,000 because there's no hydrogen. It's effectively. Yeah.
Based on these models, at what wavelength do you expect it to be optically thin?
We don't know. We have yet to find the wavelength where the atmosphere becomes optically thin, and we observe out to, so yeah, data are spectroscopic as well. So we observed out to we reported our data out to 12 microns. So this was MIRI LRS that we observed with, that was the instrument mode. We have spectra from 5 to 12 microns at every orbital phase. So this is just taking two of the orbital phases, the day side orbital phase and the night side orbital phase, and comparing to the spectra that are produced by each of those general circulation models that I showed in white light, basically bolometric in the previous plot. So the interesting thing here is that we get kind of so basically blue line and blue line, right? Those come from the same 3D model. So those are tied to one. Those are one model. Those are tied together. And we get a pretty consistent picture where we can fit both the day side and the night side spectrum well if we again include a thick haze and a high metallicity of 300 to a few thousand times solar. We also, the day side looks pretty close to black body, although there's a tentative spectral feature here. The night side definitely has a clear non-black body spectrum. We have an absorption feature. At such low resolution, it's hard to say exactly what it is. It's consistent with water, but it's also consistent with nearly consistent with methane. It's more consistent with water, but it really could be either or.
And just to get this straight in my head, you are changing the metallicity by, multiple orders of magnitude, and the haze is enough to bury any of those changes in the transmission spectrum. Because normally I would have said, oh, you're changing the metallicity by some massive amount, you're going to see features in the transmission spectrum.
So yes, so when we are turning those knobs independently. By turning up the metallicity, the effect that has on the transmission spectrum is to flatten it because you're reducing the scale height. So you actually don't need as much haze in the high metallicity case to produce the flat transmission spectrum. But the transmission spectra data, when you put all the all the HST plus JWST together also implies that you need that this planet has a metallicity of at least a few hundred times solar. Yeah, so this is probably not a hydrogen dominated atmosphere. This is a heavy molecule dominated atmosphere. We got to have a press release. JPL put together this nice image for us that's supposed to denote hazy atmosphere with thermal emissions shining through. This is maybe better. So yeah, this came from Twitter, from Jesse Christensen, right? This is the reflective mirror ball planet, because its inferred albedo is something like 0.5, very high. And then again, getting back at what the planet is in bulk.
Sorry, why haze not ice?
Too hot, way too hot for ice. So this planet has an equilibrium temperature of like 600 Kelvin. Yeah, so that's why the hydrocarbon hazes will happily exist at that temperature. Yes, and so you think about hydrocarbons, or you think about soot. Soot is dark. So this is the next mystery, is what's so bright. Yeah, we have some ideas. All right, so in terms of what this planet is in bulk, again, looking at interior structure models for this planet, coupled together with our understanding that now the atmosphere of this planet has to be at least a few hundred times solar metallicity and very hazy. What we find, what Matt Nixon finds, is that the implied hydrogen mass fraction in the planet is up to a few percent, but also the implied water mass fraction in this planet is probably a few tens of percent. So this is not the classic water world, which is just water, rock, ice. This is not the classic gas dwarf, which is just hydrogen, rock, iron. So this is neither nor. This is some sort of new, maybe combined hybrid kind of planet. All right, last planet I want to talk about. I'm going to cover this one really briefly, but I want to talk quickly about the magma ocean aspect. It's TOI 270d. So now we're stepping down in temperature again, back down to a low enough level of irradiation that we're getting to planets where we see clear atmospheres again. We don't see the haze. So clear atmosphere, beautiful features, lots of them. The gases that are confidently detected here are methane and CO2 and water vapor, although the water is a little bit hidden in the spectrum actually, but it is confidently detected. And again, the fun is, we have this beautiful spectrum. Oh, by the way, this is the first sub-Neptune where we've been able to get a constrained measurement on the carbon to oxygen ratio, because we actually detected or have good upper limits on the abundances of all the carbon, the main carbon and oxygen bearing molecules. So this is the kind of work that we've done previously for hot Jupiters. This is what we want to do for lots of sub-Neptunes. We've done it now for one. So the inferred metallicity of this atmosphere is about 200 times solar, another high metallicity atmosphere, and it seems to have a solar carbon to oxygen ratio, which is interesting. All right, so what is this planet? Let's think about the magma ocean interactions. So if the atmosphere, the envelope, overlies a molten silicate layer, a magma ocean, you're going to have chemical exchange between the magma and the atmosphere. So we used a model where we allowed for, we just put a primordial, just hydrogen helium atmosphere on top of a silicate magma ocean and a metallic iron core. And we allow for chemical exchange between these layers. And so the really interesting thing is that starting with that solar composition mixture of gases in the atmosphere, the exchange between, so the hydrogen basically reacts with the silicates, and you produce water in the interior, but it also outgases back into the atmosphere. You produce a lot of water. So this model predicts very high abundances, 10+% water vapor, even though we just started effectively with nearly just pure hydrogen helium. And it also predicts comparable amounts of methane and CO2 and water to what was actually seen in the transmission spectrum for this planet. So this is saying that just a magma ocean interacting with a primordial atmosphere can reproduce the JWST observations without needing to incorporate large amounts of water ice at formation for this planet. So it's another way of building a planet that might look like a water world or a water soot world, without needing those materials at when the planet was formed. Interesting. Oh yeah, and then here's so this model of the atmospheric composition now mapped onto the transmission spectrum. It reproduces the data really exquisitely, and this is not a tuned model really almost in any way. Okay, so the magma oceans might play a major role in setting the atmospheric composition of sub-Neptunes. This is again a new picture that the community, the field, has just recently started considering the possible implications of a magma ocean in contact with an atmosphere. But now, again, this is now the work of a former undergrad, Bodhi Breza, has been working with Matt Nixon, my former postdoc, realized that maybe not all of these sub-Neptunes even have magma oceans. This was a model that Matt had previously run for GJ1214b. And so this is the temperature pressure profile that he predicts for the planet's atmosphere, all the way down to the base of the atmosphere. So this is the filled circle is the atmosphere mantle boundary. And if you compare that to a phase diagram for silicates, you find that you're actually now, because you're at such high pressure at the base of the atmosphere, you're in the solid phase of the silicates, not the liquid magma phase. So this implies that at least for this planet, because of its thick, heavy atmosphere, you might not have a magma ocean at all. You might have a kind of classic solid surface. So we need to map out the parameter space of sub-Neptunes over which you would expect that magma ocean to be alive and well and interacting with the atmosphere versus those that would have the magma ocean basically frozen out due to high pressure.
And you say magma ocean, does that mean it's liquid, or that means
It's liquid.
there's not another layer between that and the atmosphere?
It means it's liquid.
Just liquid.
Yeah.
Okay.
Yeah.
Not where it is.
Yeah. You'll have chemical exchange between the liquid and the overlying gas much more readily than you'll have chemical exchange between a solid, and the solid and the gas is a more difficult membrane to exchange across. Oh, sorry. Right, and this is mapping out. So they did this work to map out the parameter space over which you would expect solidification of magma oceans, and they find that high pressure envelopes and high mean molecular weight envelopes lead to magma ocean solidification of the blue regions. All right, so I'll summarize quickly because we're basically out of time. Where are we at today with JWST studies of sub-Neptune atmospheres? So I showed you 3 cases, but then other planets observed. So this is now revisiting that parabolic potential haze trend with some new JWST data points. And we can see that trend still seems to, at least at first, hold up, where we have the hazier atmospheres at moderate equilibrium temperatures and the clear atmospheres at higher and lower temperatures. So we'll keep pushing on that. There are many more sub-Neptunes across this whole temperature parameter space that have been and will be observed with JWST. And then these high mean molecular weight atmospheres also seem to be a fairly common outcome so high metallicity, high mean molecular weight atmospheres seem to be a common outcome for the sub-Neptunes that we've studied. So everything here shown in that open circle has an inferred high mean molecular weight greater than 5 atomic mass units. So that's something like at least 100 times solar metallicity. with TOI 421b, that first planet that I talked about being the exception, where it has a low mean molecular weight atmosphere, and that may have to do with the fact that the planet's hotter, that may have to do with the fact that the planet orbits earlier type host star, so it formed differently, or that might just be compositional diversity. We don't know yet.
And since you had K218b on this plot, and I cannot help but ask about Madhu's paper, what is the story now with dimethyl sulfide and whether or not that is actually present in that?
There is no conclusive evidence for DMS in the atmosphere of K218b. There are multiple papers that show that very clearly. Yeah, it could be there, but there is not conclusive observational evidence that shows that. Okay, so yeah, just to sum up, JWST is finally allowing for detailed studies of sub-Neptune atmospheres. The aerosol occurrence rate seems to follow a temperature-dependent trend that is consistent with hydrocarbon hazes, but we're still trying to map out the parameter space over which those aerosols do and don't occur to really pin down what the aerosol formation mechanism is. At least some of the sub-Neptunes have high mean molecular weight atmospheres, so we're trying to understand if that is due to the existence of water worlds, water soot worlds, miscible envelopes, so atmospheres that are water and hydrogen mixed, magma ocean interactions. These are all plausible explanations, so we need more observations to try to distinguish between these different, all of these different scenarios. And then the dominant sub-Neptune formation pathway is still uncertain, but most of the sub-Neptunes that we've observed, their atmospheres are inconsistent with pure primordial primary atmospheres, with TOI 421b being a notable exception. And I'll just finish up by saying that that I do think that population level studies of sub-Neptune atmospheres are the way to go in distinguishing between the relative roles of all of these different processes that I've talked about, because it's just really hard to do on a single planet basis.
We have some time for questions. Can I speak?
Thank you, very nice talk. This might be a slightly irrelevant question. Neptune was only visited once, 1989, and I'm wondering if this work would benefit from another visit to Neptune, or vice versa. If a visit to Neptune might inform the work.
Yeah, I mean, I think visits to Neptune or Uranus would be useful, you know. Also Venus, also Titan, they all have, they all hold certain parallels to sub-Neptune environments, and certain, key differences. So with Neptune and Uranus, I think, anything that would better constrain their interior structure would be maybe especially interesting for understanding sub-Neptune interior structure, although the sub-Neptunes are a lot hotter, and that does make a difference.
Charles?
I was wondering what the prospects are for understanding visits from first principles. Can you just talk a little bit about the challenges and?
Yeah, so the main challenge is that the set of chemical reactions that gives rise to a hydrocarbon aerosol is very complex. So there's a whole field of combustion chemistry, and the combustion chemists don't have the reaction networks that go all the way to soot. People who study Titan, they don't have the reaction networks that go all the way to Titan's aerosols. The prospects for getting there are, I think, not great. So we need to figure out, what pieces we don't understand. So I wish I had this plot. There's kind of a there's stepwise processes that you go from small molecules to larger gas phase hydrocarbons to small particles to like fractal aggregates. And so from talking with my postdoc, one of the pieces that's maybe most poorly understood is the gas phase to particles and the first stage of particle growth. That's something that's probably best addressed through lab studies. And also the lab studies that have been done are typically, I mean, for their combustion studies for like engines. So that's not a sub-Neptune atmosphere. There are some experiments that have been done at Titan-like conditions. That's a cold nitrogen dominated atmosphere. So that's not a sub-Neptune. So doing experiments that are more tied to a sub-Neptune-like atmospheric composition would be very useful.
So is it actually possible to mimic the conditions in the atmosphere of a sub-Neptune in a laboratory on Earth? Because given like the great pressure and temperature involved.
In the observable atmosphere, it is doable. So Sarah Hurst at Johns Hopkins has a haze chamber where she tries to form hazes at sub-Neptune-like compositions. She's one of the only people who's done sub-Neptune-like compositions because hydrogen combustible. Most labs won't go near a hydrogen-rich mixture of gases, but yeah, she's gone up to, I think she's gone up to like 12, maybe to like 1200 Kelvin. The deep atmosphere in the interior is also interesting from a lab perspective, understanding the equation of state of materials under pressure in deeper in a sub-Neptune interior. You get up to pressures that are difficult to impossible to simulate in a lab. So that's kind of another experimental frontier on in understanding the interior structure of sub-Neptunes, and that is directly relevant to what we see in the atmospheres.
Yeah, actually.
Yeah, very nice talking. I was curious, I guess on the computational simulation side, you mentioned that there are some pretty there are a lot of challenges in actually like enumerating all these types of configurations. And I was just curious if you could comment on that and if there are paths forward to like.
So there's hierarchies of models. So I mean, the kinds of, so I mean, I run a lot of one-dimensional models where we just assume a atmospheric column, it has a composition, it has a surface pressure. You just do rate of transfer through the column. That's fast. But if you want to predict, I mean, it takes a hydro model to predict atmospheric circulation. So that was what I was referring to with the general circulation models. Yeah, those are slow and can take like a month on a cluster. Yeah, so the chemical kinetics models where you're following all the chemical reaction rates, those can be slow and just difficult to converge. It's like stiff differential equations. So yeah, those are kind of the 3D models, the 3D hydro models and the chemical kinetics models are two places where we're somewhat computationally limited. Also running the retrievals, so to find the best fit parameters that match the data, the spectrum, given the whole parameter space of possible atmospheric compositions, right? You need to run thousands, tens of thousands of individual models and do a whole, Bayesian like nested sampling fit that with JWST quality data and lots of spectral data points, that can also be very slow, even on a cluster GPU accelerating these codes, and that's helped. But yeah, that's also a computational hurdle, I would say.
Some of this sounds vaguely reminiscent of like supernova simulations, the challenges there. But anyway,
yeah, so we can still speed up some of these codes a fair bit. We've like with the JWST data, we've only reached the point where now we really need to. Yeah.
Just because you mentioned like population statistics, because it seems like Webb is really good at characterizing these atmospheres on individual level. But how long is it going to take to actually get those population statistics on your mind?
So there's already, gosh, we've probably had 100 exoplanet atmospheres already observed with JWST, and a few tens of atmospheres of sub-Neptunes even observed with JWST. The data sets are still, it's kind of bespoke analysis, so it takes time. There's lots of public data sets that are not actually published data sets yet. It's taking time to get the publications out. The other issue is that because it's all general observer proposals, it's a scattershot of data sets. So it's like this small planet observed at shorter wavelengths, and this bigger planet observed at longer wavelengths, and this one we observed multiple times because we wanted to get higher signal to noise, and this one we just observed once. And so it kind of putting that all together, it is not even close to a uniform data set. And so that presents its own challenges.
And if I can ask the last one, you set the big questions out as formation, evolution, and habitability. And we
Yeah.
haven't talked yet about habitability, which I'm sure has
Oh, sure.
carbon and hydrogen and sulfur
Mhm.
and said, now solid mantles potentially magma oceans. So what would be the smoking gun?
Oh gosh, smoking gun is still hard because you need the context. So even if you see oxygen, like O2 in an exoplanet atmosphere, or O3, you're not gonna do a JWST, but you still need the context of what else is in that atmosphere. DMS, so my chemist postdoc, Jayun, even if it is there in K218b, he found an abiotic chemical pathway to produce DMS. So the idea was that this is a smoking gun biosignature, and then we have the chemist who says, I can show that it's not. So yeah, that's the trick. I'd say the first thing is to try to find just evidence of habitable environments before we jump straight to biosignatures. Yeah.
Well, if there are no other questions, let's thank our speaker again. Bobby around 5:30 and go to place of choosing nearby.
Yeah.